Welcome to the Problems Channel Season 2, Episode 47, the episode which I titled Non-Square Square Grasshoppers, because in this episode we will solve a beautiful problem that deals with three grasshoppers jumping over the so-called orthogonal integer lattice Z squared. But before we deep dive into the underlying mathematics, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to get your bearings on our channel, figure out what is going on, and the most efficient way to derive the most academic benefit for yourself from working with the material presented on this channel is to go to the homepage of this channel and in the channel's trailer section find the episode titled The Problems Channel How To. Watch that episode in its entirety, follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. In the mathematical problem S2E47, we're given three grasshoppers that initially sit in three distinct vertices of a unit square. And apparently it is not specified in which concrete configuration, but because we have one grasshopper sitting in each vertex of a unit square, the number of different initial states is not that much. For example, one sample such initial state is shown on the board over here. One grasshopper can sit, for example, shown in blue over here in the lower left corner of a unit square. One grasshopper can sit in the lower right vertex of a unit square, shown as a blue dot over here. And one grasshopper can sit in the upper right corner of a unit square as shown with the blue disk over here. And evidently we can obtain all the initial configurations of these here three grasshoppers by rotating this configuration shown over here around the center in the parent plane counterclockwise by pi over 2 radians or by 90 degrees, so that we have the three grasshoppers sitting, for example, here, here, and here, 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 and here, and here, here, and here. Apparently that doesn't matter. Any initial configuration will do. Then every second, let's say it doesn't really matter, every minute, every hour, every your favorite unit of time, but let's say for definitiveness, every second, any one grasshopper, so we can say a random grasshopper, it can be this one or this one or this one, executes one jump over any other grasshopper, or he can make a choice, he or she can make a choice between the remaining two. For example, let's say this grasshopper decides to jump. Well, then that grasshopper has two choices. It can jump over this grasshopper or over that grasshopper. It doesn't really matter. The choice is, again, let's say random. And the jump is executed as follows. The grasshopper that jumps over another grasshopper flies over the stationary grasshopper the distance that is precisely equal to the distance that initially separated the two grasshoppers. So in this configuration, I have shown all the possibilities that can take place after the initial configuration is set as shown over here. The timer is started, the clock is ticking, and the jumps begin. For example, the grasshopper shown on your left, the lower left, let's say grasshopper can jump which way? He can jump over the lower right grasshopper by the distance 1 and find him or herself over here. This is one possible jump. Or that grasshopper can jump over this one, but in this case it will land on the point that is how many units of distance away? Square root of 2. This is 1, this is 1, right isosceles triangle, this distance is a square 2. So if this grasshopper decides to jump, then this grasshopper will fly the distance of what? Square root of 2 to the stationary grasshopper and another square root of 2 to this point over here. Likewise, this grasshopper can jump over this one lower left or over this one, and this grasshopper can jump over the grasshopper stationary lower left or over right. And every time, again, the rule that is specified and cast in stone is that the jump that every grasshopper executes amounts to a flight over the stationary grasshopper that is equal in distance to the distance that separated the two grasshoppers initially. And the challenge or the question in this problem is the following: can it so happen that in a finite number of seconds, in a finite amount of time, or in a finite number of legal jumps, these three grasshoppers will find themselves at the three distinct, evidently, vertices of a 2 by 2 square? Not 1 by 1, but 2 by 2. And evidently, precisely because of the placement of this problem in our sequence, it should be obvious to all the viewers of our channel who watch our channel on the regular basis that this problem can be solved using the invariant problem solving approach. I already explained how the invariant problem solving approach works in season 2, episode 44. If any of you guys missed my explanation, you may want to find this episode and watch that episode in its entirety, because this is where I give the detailed explanation of how the invariant problem solving approach works. But here is a lightning version of it. If we want to apply the invariant problem solving approach to the process of generating a solution to this or that technical problem, we should try to partition the local material into two distinct piles. Into one pile we put all the material, all the local material that does vary, and into the other pile, usually much smaller in size, we put everything that does not vary. All the things that do not vary under the local circumstance we refer to as an invariant with respect to. We already know by now that not all invariants are created equal, in the sense that some invariants are more useful, tactically more useful than others. And overall idea here is the following: roll through all the invariants in the second pile that we identified and try to leverage the invariance of certain quantities in the local circumstance in order to generate a solution of the problem. So far we have seen already in two problems that we can come up with a certain quantity that remains invariant, and that means that we can compute that magnitude of that invariant for the initial state of the problem. Then, precisely because that quantity is conserved or remains invariant after every step in a process, then evidently when and if the process terminates, then we can compute again the magnitude of this invariant and compare it to the magnitude of the proposed invariant that applies to the target or requested configuration. And then we can, for example, either produce a contradiction or show that, yes, look, this is what it is, and that configuration or that scenario is possible. And in mathematics, these things work actually, or amazingly enough, precisely the way they work in physics. For example, if we can prove that in a given system, for example, the linear momentum is conserved, then we know that the amount of that linear momentum before an interaction and after an interaction is one and the same. We construct the corresponding equations and boom, we hopefully solve a problem. If we know that in this particular problem, for example, the angular momentum is conserved, then we know that the magnitude of the angular momentum before an event of interest and the angular momentum after the event of interest is one and the same. We equate the two and we derive a tactical benefit and use this as a stepping stone in our solution. Also, likewise, for example, if the total mechanical energy is conserved, then we know that the total amount of energy before something interesting happens and after something interesting happens is the same. We equate the two and we usually again use that as a stepping stone in the process of generating a solution of the problem at hand. This is the big plan, the bird's eye view of how the invariant problem solving approach works. And in addition, this here problem is again an open-ended problem. And we, from our previous episode, we remember that a technical problem is open-ended if and only if it does not, specifically does not contain a precise outcome in its statement. In other words, in this problem over here, we're not told that the three grasshoppers, after they jump around the way it was described, they can find themselves at the vertices, three distinct vertices of a 2 by 2 square. And we are also not told that they cannot. That choice is up to us. In other words, in this case, if we think that the answer to the problem is in the positive, then the burden of producing at least one winning sequence of legal jumps, following which, from the initial state, three grasshoppers will find themselves in three distinct vertices of a 2 by 2 square, is on us. We have to think about it and say, hey, look, if we take the three grasshoppers, each sitting in one distinct vertex of a given unit square, any which way, if any one of four possible initial states. And then, for example, we number the grasshoppers 1, 2, 3, and then we write down the algorithm. The grasshopper 1 jumps over the grasshopper 2, the grasshopper 2 jumps over the grasshopper 3, bam, 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 in a finite number of steps. Look, the three distinct vertices in which these three grasshoppers find themselves are precisely the vertices of a 2 by 2 square. We have to produce that legal algorithm, if you will, or legal sequence of jumps. If we think that the answer to this problem is in the negative, then we have to generate a convincing proof that no matter how these three grasshoppers jump around as per the rules described, then there is absolutely no way that they can find themselves at the vertices, at three distinct vertices of a 2 by 2 square. That burden is, again, but the burden is on us, but again, this choice of which way this problem goes is not given to us. We have to make that choice and we have to decide what is the outcome. But again, the viewers who are the regular customers on our channel already understand that the hint to the answer of this problem is precisely in the title of this episode: non-square square grasshoppers. Which exactly means that now is a good time for those of our viewers who could not solve this problem correctly and on their own to put this video on pause, take in the hint that's in the title of this episode and try to solve this problem on your own, walk away from the computer and then come back, compare your ideas to ours. Meanwhile, we applying the invariant problem solving approach to the process of generating a solution to this here problem. We'll try to look at things that do vary. Before we do that, however, a small discussion about in real time what is the right thing to do. Look for things that do change or look for things that do not change right away. In my experience, I find that in general, it doesn't really matter. If you think that you want to jump feet first into looking for things that do not change, then by all means go right ahead. But in my experience, again, I find sometimes it is useful to first analyze things that do not change, because sometimes in this or that technical problem, it may so happen that the number of things that do change is somewhat nicely balanced with the number of things or the amount of things that do not change. Sometimes the things that vary just too big, too much in scope, and then either way, the situation that goes on with things that do change may actually point us toward the things that do not change. So in this case, in this situation, let us think together what does or what can change in this problem as our grasshoppers begin executing their legal jumps. First thing that comes to mind, the thing that we notice right away, is that the distance between the three grasshoppers may change. For example, let's say the grasshopper number 1, or the leftmost grasshopper, the grasshopper that sits at the lower left corner of our unit square, initially jumps over here into this point. He flies the distance 1 over the stationary that separates this grasshopper from the stationary grasshopper, and another distance past the stationary grasshopper. Then initially, what type of what was the distance between all three grasshoppers? Well, the distance between all three grasshoppers can be described with a triplet of real numbers, 1, 1, and then square root of 2. And after that jump, after the first grasshopper finds itself over here, what is the distance between these three grasshoppers? Well, it's the same essentially triplet of real numbers, 1, 1, square root of 2. So in this case, the distance between the three grasshoppers pairwise in this way did not change. However, if, for example, the same grasshopper jumps over the upper right grasshopper over here, then what will be the distances between the three grasshoppers? Well, the distance between the stationary grasshoppers obviously will not change, but the distance between the jumping grasshopper, the grasshopper that just executed the jump, and this one will be what? This weight will run this way. What will this distance be? Well, 1 and 1, 2 squared, 4 plus 1 squared, 5, square root of 5. So the distance will be 1. This distance will obviously be the same, square root of 2, but this distance from here to here will be already square root of 5. So the distance between the grasshoppers in this case did change, or in this case we can say it does vary. What else can change? Well, for example, the exact shape of the triangle that is formed by the points in the plane in which the grasshoppers find themselves after the appropriate jump has been executed. For example, let's see. Initially, in our case, what is the shape of the triangle that we have? Well, this is an isosceles right triangle, and as in the first case, if the grasshopper that sits in the lower left corner of the unit square jumps over the grasshopper that sits in the lower right corner of the unit square, what do we get? We get essentially a congruent isosceles right triangle. So in this case, the shape of the triangles which are formed by the three grasshoppers before the jump and after the jump did not change. Yes, but again, if our grasshopper here that sits in the lower left corner of the unit square jumps over the grasshopper that sits in the upper right corner and finds him or herself in this point over here, then what do we have? Well, in this case, we will still have a triangle, but this time, what are the vertices of this triangle? This one, and this one. And is this triangle isosceles and right? The answer evidently no. The new triangle is not isosceles, it's not right. The length of this side is 1, the length of this side is square root of 2, the length of this side is square root of 5. Square root of 5. The lengths of all three sides are different positive real numbers evidently, so the shape of the triangle, let me cross hatch it like this, see? The shape of this triangle compared to this triangle over here, what did change? So that shape does vary. Also, some other things may vary over here. If you guys notice something that can change from jump to jump, don't be shy, share your ideas with our community in the comment section. But gunning towards the material that does not change, and as another small hint for you guys, actually a number of things are invariant in this case, of various depth, of mathematical depth and heft, and we will discuss some of these things. But working towards the material that does not change, the bright idea over here is the following. As we experiment or play with the possible configurations of the grasshoppers, with the possible legal configurations of the grasshoppers as the jumps in the plane unfold, an interesting question that points us in the right direction is the following. What is the nature, or in some sense, what is the structure of the points where the grasshoppers can find themselves after any legal jump? And the answer to that question comes in the form of a device that in grown-up mathematics is known as orthogonal integer lattice, designated, let's see if I can capture the blackboard letter Z. Z is squared like so, and it is constructed as follows. An orthogonal integer lattice Z squared can be generated in a number of ways, and here is one such way. We can intersect two families of parallel straight lines as follows, for example. We can take one family of logically vertical straight lines, each of which is parallel pairwise with all the other straight lines, shown over here on the left side, and we can intersect that family of vertical or logically vertical parallel straight lines with another family of logically horizontal parallel straight lines, or a family of straight lines which run horizontally like so and which are perpendicular. Each such straight line is perpendicular to every straight line from the vertical family of parallel straight lines, and evidently both families of straight lines are spaced apart, or any two immediate neighbors in each family are spaced apart by precisely 1 unit of distance. So 1 unit of distance vertically, 1 unit of distance horizontally. The angles are all right, and it is important to understand that in that method of generating an orthogonal integer lattice Z squared, the straight line themselves are normally not taken to be part of the lattice. What does form this specific lattice is precisely the points of intersection of these two families of straight lines shown over here. So here and that is why for demonstration purposes, guys, I showed the straight lines only partially on the left-hand side of the lattice, and I did not show any straight lines on the right-hand side of the board over here, because again, the straight lines that generate the points of intersection are not a part of the lattice, but the points where the straight lines intersect are the orthogonal integer lattice Z squared. That is one way to generate such a lattice, and that lattice can be generated in a number of different ways. For example, one such way is to take any, let's say, in general, it could be any parallelogram, for example, this way. And this parallelogram in this case will be called, it can have several different but essentially the same in meaning ways. It can be called prime, it can be called primitive, or it can be called a fundamental parallelogram or a generating parallelogram. And what we do with this generating fundamental or prime, if you will, parallelogram is the following. We parallel translate that parallelogram this way by the length of its one side, and we create infinitely many copies on the, let's say, logically on the right side of this parallelogram. And then we parallel translate that parallelogram in the parent plane leftward by exactly the length of this side. And we generate another infinite tiling of this portion of the plane with another infinitely many congruent parallelograms. And that way we have the strip. And then what do? Exactly, then we do the same translation, but we do it along the other side. This side, it could be different in length than this side over here in one direction, and then in the other direction. In this way, we tile the entire plane, let's say Euclidean plane, with this here prime, primitive, or fundamental generating parallelograms tight with no gaps and no overlaps. Again, using the parallelogram as a legal geometric shape is just a helper device. Technically, once we generate such a tiling of the plane, we erase the sides that form this parallelogram, and what will we have left? We will have infinitely many points, and these points become precisely the nodes of the corresponding lattice. In general case, it will not be orthogonal, and the distances in one direction and the other could be very much different, but in our case, what we have is our parallelogram becomes what? It becomes a generating square. We do the same maneuvers with the square. Tile the plane to the right, tight with no gaps and no overlaps. Tile the plane with the squares to the left, again tight with no gaps and no overlap. We take this infinite strip of squares and we tile the upper portion of the plane tight with no gaps and overlaps. And then we take that strip and tile the plane down again with no gaps and no overlaps, and thus we generate the orthogonal integer lattice Z squared. Again, we erase the sides technically, and we only keep what? We only keep the vertices of the square, which become the nodes of the lattice, and that is the essence of the lattice. In this case, this lattice has an official name in grown-up mathematics known as the orthogonal integer lattice Z squared, and such a lattice has a number of interesting and tactically useful properties. Now, in such a lattice, at any point we can pick one of the straight lines from, let's say, logically vertical family of parallel straight lines. Let's say we pick this one and we name that logically vertical straight line, for example, y-axis. And from the family of horizontal parallel straight lines, we pick also any which one, and we name it, let's say this one, we pick this one, and we name that straight line the x-axis. And it should be also understood that the directions in which this axis run also is irrelevant. We can point the y-axis logically down, and we can point the x-axis logically to the left. It doesn't really matter. This is one traditional setup. The y-axis points up, logically up. The x-axis points logically to the right. The unit distances are marked. This is 1 unit of distance along the x-axis. This is 1 unit along the y-axis. And the question here from the audience is this: okay, Roman, this is all fine and dandy, but how does it help us? Where are you going with this? Where is the invariant over here with all this fancy schmancy orthogonal integer lattices? Well, we're getting there. Now look, we place, remember our initial configuration. It doesn't really matter. You guys can place your 3 grasshoppers any which way. For demonstration purposes, I'll place these grasshoppers in these 3 corners like you saw before. So in this case, what is another useful device that we get with the orthogonal integer lattice Z squared with the chosen coordinate system? Well, we see that initially our grasshoppers sit at 3 nodes, at 3 points that have precisely integral or integer coordinates. Our grasshopper that sits in the logically lower left corner becomes the grasshopper that finds itself in the point with the coordinates 0, 0. You see? 0, 0, this guy. What is the coordinate of this guy? The coordinate of this guy is 1, 0. You see? And the coordinate of this guy is what? 1, 1. This guy is free. There is nobody here. Let's put it this way. So initially we have a grasshopper at a point with the coordinates 1, 1. One grasshopper at the point with the coordinates 1, 0, and one grasshopper at the origin of our arbitrarily chosen coordinate system with the coordinates 0, 0. Now, how does that help further? Roman, you keep talking, but where is the essence? Where is the meat? Well, here's the thing. Let's think about what type of transformation does any legal jump of one grasshopper over another represent? Put this video on pause, think on your own, but the answer is any legal jump of one grasshopper over the other corresponds to what? It corresponds to a transformation of the plane known as central symmetry. And the central symmetry is carried out with respect to what? With respect to the stationary grasshopper over which the jump is executed. Let's say in this particular case, the grasshopper that was sitting over here at a node of our lattice with the coordinates 1, 1 decides to jump over the grasshopper that is sitting at the node with the coordinates 0, 0. Then this jump corresponds to the central symmetry of the parent plane with respect to the stationary grasshopper that is being jumped over, the grasshopper that is located at the point with the coordinates 0, 0. And remember that the central symmetry of the plane is such a transformation where any point of the plane P, is taken into a point, let's say this is the center of the central symmetry O, is taken into a point P prime. Let me try to this way, P prime, such that first the points P, O, and P prime all belong to one and the same straight line, lambda, which is to say that the 3 points are collinear. And what is the second condition? That's right, the distance from the point O to the distance from the point P to the point O is the same as the distance from the point O to the point P prime. This is a definition of central symmetry. You see, it's not that complicated. These distances are the same and the 3 points are collinear. This is somewhat similar to the symmetry of the plane with respect to the circle. Over there, the 3 points are collinear, but the distances are not. The distances are constructed differently. So how does that help? Well, that helps us a lot because here is one useful property of the integer lattice that comes to view. The orthogonal integer lattice Z squared has how many centers of symmetry? It has infinitely many centers of symmetry. In other words, our orthogonal integer lattice Z squared is centrally symmetric with respect to any of its nodes. In other words, if we pick any node in our lattice, let's say this one or this one or this one, it doesn't really matter, then under the central symmetry with respect to the chosen point, any one, this one, this one, this one, this one, this one, or this one, that lattice will be taken exactly back into itself. And what does that mean? Well, that means that as our grasshoppers execute their legal jumps any which way, which points can they find themselves into? What is, remember my earlier reference to the structure of these points? Well, the structure of these points is exactly that. When our 3 grasshoppers execute their legal jumps, the only points where they can find themselves in after each and every legal jump will be precisely the nodes of the corresponding orthogonal integer lattice Z squared that is generated as I explained above. We take the unit square that was given to us initially. Remember, we are told that initially 3 grasshoppers sit at 3 distinct vertices of a unit square, 1 grasshopper per vertex of the parent square, and that square precisely becomes the generator of the corresponding orthogonal integer lattice. What we do is we translate that generating square in one direction and the other, we get the strip, we take that strip and replicate it to the upward, let's say logically, and replicate it downward, and boom, voila, we have our orthogonal integer lattice Z squared. And one key step towards the invariant, one of the invariants that we will uncover in this problem, is the following. As our grasshoppers execute their legal jumps, the only points in which they can find themselves after each and every legal jump will be precisely the nodes of the orthogonal integer lattice generated by the parent or the generating square. In other words, as our grasshoppers jump around, they cannot find themselves somewhere in the middle, here, 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 or here. No, there is no such thing. That cannot happen. The only points where every time a grasshopper jumps to will be precisely a point of the corresponding orthogonal integer lattice. And now this is another hint for you guys. Put this video on pause. In the next few seconds, we will uncover one useful invariant that will help us solve this problem in an elegant way. Here is the idea, or an idea, that you were expected to generate on your own. What we do now is that we take our given initial or generating unit square, and then we translate that square over the orthogonal integer lattice Z square over all even vectors. What is an even vector in this case? Well, let's call it the set. Let's give it the name E. And these are all the even vectors, E, K, M, that have their origin fixed at the point 0, 0, but their terminal point will have the following coordinates: plus minus 2k and plus minus 2m. Let's close this guy. We understand what that means. And then the numbers km belong to the following infinite set: 0, 1, 2, 3, and so on, or basically the infinite set of non-negative whole numbers: 0, 1, 2, 3, and so on. In the first case, evidently, when k and m are 0, we get the 0 vector. Nothing happens over here, but after that, things become interesting. In other words, these are the vectors that we call even, and we generate how many? Well, we generate infinitely many of them, but the key point of this vector, and that is why I refer to them as, loosely speaking, even vectors, is because the terminal point of each and every such vector is a point that has the coordinates, the structure of each of which is what? Is an even whole number, an integer, positive and or negative. So now what happens over here is the following. As we translate our square, our parent unit square, along all the even vectors, parallel translation is a type of rigid motion that preserves the distance between any 2 points of the object that is being transformed. And that means that when the generating square is translated that way, all the points, or the 4 vertices that delineate the square, also travel uniformly with that square. As such, let us see what happens if we, let's say, fix our coordinate, the number m, let's say the vertical displacement as 0. We set m equal to 0, and we start varying k. Again, when k is 0, we get the 0 point. I will mark it in red. I hope you guys can see it, but this is red. And again, the image that you saw at the beginning of this segment shows you what's going on, and you should, it's a good idea for you guys to trail what I do in your favorite graphing software. Do not be lazy, generate that coloring of the lattice that will happen. But what is the next point? What is the next non-trivial, non-zero vector that will come out from this set of even vectors? Well, when m is 0, then the vertical displacement of every point in our lattice will be 0. That means that every, let's say, red point will be sitting on the x-axis. And in what steps will this red points grow on that axis? Well, in steps of 2. When k is 1, what is the coordinate of the, let's say, first even vector? Well, it will be plus 2, 0, and another one will be minus 2, 0. So we get a red point over here, and we get a red point over here, and then we get a red point over here, and then we get a red point over here. You see, this is how these things work. It's not really complicated. Now we bump up m by 1, and that means that we pushed our point we peeled it off the real axis, of the x-axis over here, and we jump into the plane now bravely. But where do we jump? Well, when m is 1, then the y component of each coordinate of a red point will be what? It will be +2 something and then -2 and something. And what would that be? Well, with k equals 0, we get 0 +2, 0 -2. So we get a red point here, and we get a red point evidently over here. And in each proverbial straight line that belongs to the family of logically horizontal lines, we get another red point where? Here and here. We get another red point here and here. We get another point where? Here and here, and let's say here and here. You see how these things work? It's not really that complicated. You guys should really carry out this construction yourself just to develop a feel. But now think about it. You can play with numbers, with the algebra of the coordinates of our even vectors. It's always a good idea, but we can, in this case, once we understand what's going on, we can generate this, let's say logically or loosely speaking, four-coloring of our orthogonal integer lattice quite mechanically by envisioning that we grab our unit square and then we color all its vertices, all four vertices, in four distinct colors. Let's say red, this is green. If you guys cannot really see it that well, let's say this will be green. What other colors do I have? I have, let's say, yellow. The upper right will be yellow. I hope you guys can see distinguish yellow. And let's say the free, in my case, the free vertex will be blue. You see? So we have four distinct colors, one color per vertex of the given unit or generating square: red, green, yellow, blue. So now as we translate our generating square, unit square, over the corresponding orthogonal integer lattice by all the even vectors, again, like I said, you can run through the algebra. It never hurts. Fix one, vary the other, or if you will, you can fix this guy, the x coordinate, and vary the y coordinate. It doesn't really matter. But you will quickly catch on to the fact that you can visually simply move the entire square with the colored points in one direction by an even amount along the x direction and by even amount along the y direction, and color the vertices accordingly. Let's do that together. For example, what will happen? Let's generate the family of the green points over here. Two units of distance displacement along the x-axis. So this guy goes here. This will be green. So this one, when we translate it here, green, right? Green. And then if we translated our square by 2 units over here, so this point will be green and this point will be green. This point will be green, and which one? You see, this point will be green. In some sense, if you care to introduce, and actually in complex analysis and complex numbers, you will deal with 3 points that determine, if you will, a direction. The 3 points that can determine the clockwise or counterclockwise direction. With the machinery of complex numbers, that can be done, but here we can do it this way. If we walk in such a way along the perimeter of our parent unit square, we always have our left hand dipping inside the square. Then which colors will we see? Red, green, yellow, blue. So we have red, green, yellow, blue, red, green, yellow, blue. So mechanically you can throw all these points right away. So let's do a couple more. So if we translated the red point here, so this is green, this is green. Do I have any more room for green? So if we move this square over here, so this will be green and this will be green. You see? All right, let's do the yellow points. So the yellow points come where? Here, and then they will come here. If we move this square down over here, the yellow point will be here, this is yellow, this is yellow, this will be yellow, and this will be yellow, and then what? This will be yellow. Let's color. This will be yellow. What else? This will be yellow, and this will be yellow. Do I have any more room? Let's say yes, we will have this point will be yellow, and this point will be yellow. But you guys catching on to what's going on, I hope. So now let's do the blue points. Let's say we translated the given unit square this way, so the blue point got taken into here. You see, blue, blue. Likewise, translate this guy over here, blue, blue. So we translate this guy, the unit square, down. So this becomes blue, this becomes blue, this becomes blue, and this becomes blue, this becomes blue, 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 another blue point, another blue point, and you get the idea. So now that we have our coloring of the orthogonal integer lattice Z square, what do we see? Well, we see that the invariant in this case will be what? An invariant in this case will be grasshopper specific. As I finish coloring our orthogonal integer lattice that I started in the previous segment, I just filled in the blue coloring here at the bottom and the yellow one you can see here, and on the top. You guys think on your feet. What is the invariant in this case, and what quantity will be grasshopper specific? We came up close and personal with that invariant. We, so to speak, crossed the blades with the pirate face to face. The blades cling, cling. We can hear the blades cling. The sparks are flying. Put the video on pause. Walk away, think on your own, and generate your idea, compare your idea to ours. But here is one invariant of several that you were expected to uncover on your own. Write down this material over here. I'm about to erase it because I will need the board, but it's not too complicated. All even vectors are basically all the vectors that have origin fixed at the point with the coordinate 0, 0, and whose terminal points have the structure of even whole numbers for their x and y components. This is all there is to it. So now let's assume for a moment that, well, we already proved that when our grasshoppers execute legal jumps, the only points in the parent plane that they can find themselves must be precisely the nodes of the corresponding orthogonal integer lattice generated by the parent unit square. They cannot, our grasshoppers cannot land here, 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 or anywhere else. It has to be precisely one of the nodes of our orthogonal integer lattice. So let us assume for demonstration purposes that, let's say, one grasshopper that is about to fly is sitting at a node of our lattice with the coordinates k and m. Another grasshopper that will be stationary sits at the node of the lattice with the coordinates a, b, and then according to our rules, our flying grasshopper will jump which way? It will jump roughly, let's say, this way, so somewhere over here, and that point will be a node of our lattice with the coordinates kd for destination and md for destination. So now the question is, what is the structure of these components of the coordinate of the destination point as it is expressed in terms of the material of the components of the coordinates of the nodes of our lattice that are involved in the jump? Well, that is very straightforward to come up with. let's take a look at this. The horizontal component, the coordinate of the horizontal component in this case of the destination point will be what? The horizontal displacement of the destination point with respect to the point where the stationary grasshopper sits is the same as the horizontal displacement of the point where the stationary grasshopper sits and the point from which our flying grasshopper takes off. And what is this distance? This distance and this distance. This one or this one, it doesn't matter. What is this distance? Well, it's A minus K. Would you agree? A minus K. And then what is the KD component here in this case? Well, A plus A minus K, which is 2A minus K. This is all there is to it. And what is the Y component? The vertical component MD of the destination point. The same deal. The vertical displacement, this piece right here, this distance right here, of the destination point with respect to the point where the stationary grasshopper is exactly the same as the vertical displacement of the point where the stationary grasshopper sits with respect to the point from which the flying grasshopper takes off. This one right here, this distance. These distances are exactly the same. So what is the coordinate MD? Well, it's the coordinate B plus the displacement, the vertical displacement of corresponding points with respect to each other. B minus M. So that will be 2B minus M. And what does it tell you already? Well, there are two invariants over here. If we take any whole number, be that number positive, negative, or 0, and multiply that number by -1, will we change the parity of that number? No, we will not. The parity of such a whole number remains invariant under the operation of multiplication by -1. And once we take such an integral quantity and add an even quantity to it, will that change the parity? The answer is again no. The parity of a given number remains invariant under the operation of adding to that number, or actually subtracting from that number, an even quantity. Look at this. 2A and 2B is an even quantity. And what does that mean? That means that the structure of the components of the origin point and the destination point of the flying of any flying grasshopper, when it comes to parity, remains what? One and the same. That means that if whatever the parity of the x component of the origin point was, it will be exactly the same parity of the same component in the destination point, and the y component as well. Whatever the parity of the y component was at the origin, it will be exactly the same parity of the y component at the destination. You see, this is the key observation. And what does that mean? Well, that means that if we assign a unique color to each one of our 3 grasshoppers, and for demonstration purposes I placed them this specific way. You guys can play with any other placement, it doesn't matter. But let's say the grasshopper that was sitting originally at the lower left vertex of our unit square will be called red, because that grasshopper is sitting at the red point, the color red. The grasshopper that sits at the lower right vertex of the given unit square will be green. We'll call that grasshopper green. And the grasshopper that was sitting in the upper right corner of the given unit square will be yellow. So what does this observation over here tell us? Well, this observation tells us that the only points in which any specifically colored grasshopper can find itself whenever it executes any legal jump must be one and the same. That means that if a red grasshopper begins hopping from a red point, it can only land in red points, only red points. Likewise, a green grasshopper that initially sits at the green point, whenever it executes any legal jump, it can land only in a point that is green in color. So it can jump, let's say, this way, or that way, or that way, and all these points will be green. Likewise, the yellow grasshopper, wherever legal jump that grasshopper executes, it will land only in the yellow colored node of our lattice. For example, this way, or that way, all these points are yellow. And so let us, you guys understand where this came from. So let me erase this. Let us capture this more formally, symbolically. We don't really have to, but we will, just to be diligent students of mathematics. Let's capture this idea symbolically. Some students like symbols a lot, so let's give them some symbols. As such, let's begin with the red grasshopper. What is the structure of the red points? The structure of the red points is the following: plus minus 2k plus minus 2m for the y component, x component, y component. Let's say with the letter E, we designate the parity E for even, and this one is evidently even. Awesome. Which one is the next one? Let's do the green one next, right? Let's do this guy. What is the structure of the green points? The green points have the following structure. We see that vertically, the green points are displaced with respect to the x-axis in the same way in which the red points are displaced. That means that the y components of all the green points will be the same as the y components of the red points. And what are these components? They're 2m. But the x component, the horizontal displacement of all the green points, is technically off by 1, if you will, with respect to the red points. So how would we capture this? Plus minus 2k plus 1 for the x components, plus minus 2m for the y components. And if we were to assign parities to these numbers, just to capture this succinctly, what will it be? This will be O for odd, and this will be E for even. Wonderful. What is the next point? Yellow. Where's my yellow chap? So let's do the yellow points. What is the structure of the yellow points? The structure of the yellow points, forever and ever, again, you can reason the same way. The yellow point here is displaced from the x-axis by the same amount as it is displayed from the y-axis, so it's off by 1 both horizontally and vertically with respect to the red point. So what is the structure of the yellow points? Plus minus 2k plus 1 plus minus 2m plus 1. So in terms of odd even, what do we have? We have odd numbers for the x component and odd numbers for the y component. And just for the sake of completeness, let us do the structure of the blue points. Let's write the blue points. The structure of the blue points. What is it? Well, this time we see that the blue points have the same horizontal displacement as the red points. So far, so good. That means that the x component of the blue points is the same as the x component of the red points. Look at this. All the blue points sit on the same family of logically vertical straight lines that potentially generated this orthogonal integer lattice. So the x component will be 2 plus 2 minus 2k. But what about the y component? The y component is off by 1 with respect to the y component of the red point. So what do we write here? Here we will write plus minus 2m plus 1. And in terms of our odd even, so what do we have here? Here we have even. but for the x component, and we have odd for the y component. Now look at this nice setup over here, and you guys tell me what is the next conclusion. So we know that the color of the point or the color of the node of the corresponding orthogonal integer lattice assigned to each grasshopper cannot change. Under any legal jump, the color of the grasshopper that executes the jump will exactly coincide with the color of the node in which this grasshopper can find itself under any circumstance. So how does that help us answer the question that was posed in this problem in the first place? Under this three, let's say, these three invariants that are grasshopper specific, can these three grasshoppers in a finite number of legal jumps find themselves at three distinct vertices of a 2 by 2 square? What do you guys think? Put this video on pause, walk away from the computer, think about it, and then compare your ideas to ours. Here's a fairly deep observation that you are expected to make on your own. Notice that with our forecoloring of the underlying orthogonal integer lattice z squared, what did we create? Think about it, maybe put as a hint, put the goggles on your head that filter out all the colors but one. What will you see? Well, what you will see is the following. With our forecoloring of the underlying orthogonal integer lattice z squared, we created four sublattices and four distinct sublattices, which, when unionized, make up the original orthogonal integer lattice z squared. What does that mean? Well, let's say we put on the goggles that only can see red, and we cannot see anything else. All the other colors are gone. All other colors blind. We only can see red. What will you see? Well, you will see a sublattice whose nodes are definitely the nodes of the original orthogonal integer lattice z squared, but they are more sparse in a sense. They're not as dense, intuitively speaking, because they're all spaced 2 units apart. But look at this: red, 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 red. Square, which is what? 2 by 2. Step 2 units to the side. Again, red, red, red. 2 by 2 red square whose vertices are only red. Another red square, another red square, and so on. And you see what is going on. Now let's take these goggles off. Let's put on another goggles that can only allow us to see green. We do not see any other colors. We are any non-green color blind. But what will we see? We will see only green points. And again, these green points are definitely, most definitely, are the nodes of our original orthogonal integer lattice z squared, but they're not all nodes of the original lattice. They're also sparse, they're not as dense, they're also 2 units apart, and they also form what? Squares, 2 by 2 squares. But the vertices of such a 2 by 2 square have what color? One and the same color, green. And these, let's say green, let's call it green squares, they go in all directions, left, right, up and down, equally spaced. That is another green sublattice. Same way, take off the green goggles, put on the goggles that only show us yellow. We're all other non-yellow color blind. What we will see? We'll see the so-called yellow sublattice. Also, the nodes of that yellow sublattice are the nodes. Each and every node of a yellow sublattice is a node of our original parent orthogonal integer lattice z squared, but these nodes are not all the nodes of the parent lattice. This yellow sublattice is sparser, it's not as dense. Likewise, same deal goes for the blue points. The blue points form a blue sublattice, and once we unionize all the sublattices, the red sublattice, the green sublattice, the yellow sublattice, and the blue sublattice, and boom, we have our original orthogonal integer lattice Z square. And what does it mean? That basically means that whenever our red, green, and let's say yellow grasshoppers jump, they can only find themselves at the points whose coordinates have the parity structure shown over here. But each and every 2 by 2 square on our lattice has the vertices of which color? Well, as we just demonstrated, each and every 2 by 2 square has all 4 vertices of exactly the same color. All 4 red, or all 4 green, or all 4 yellow, or all 4 blue, which is what? Which is precisely the contradiction, because we showed that under any circumstance, the points on which the color of the points on which our colorful grasshoppers can find themselves must be precisely that. In other words, the green grasshopper, let's say, can never find itself in the red points, which it must have if it were to sit on one of the distinct 3 vertices of a 2 by 2 square that is all red. Likewise, the green grasshopper can never find itself in the yellow point. If a 2 by 2 square has to happen contain all or be constructed on 4 vertices of yellow color, this cannot happen. So this contradiction proves the fact that the answer to this problem is in the negative. In no finite amount of legal jumps, our grasshoppers can find themselves in 3 distinct vertices of a 2 by 2 square. And in some sense, you can ask me, like, Roman, why did you need to introduce the colors? Well, color is a popular device in mathematics, and look how much trouble it saves us. Yes, I wrote down all these formulas. They look nice for those who like algebra. Well, there you go. It's very explicit, but color in some sense saves us some complexity, because it is one unit of information, color. The colors are distinct, but what does the color actually hide? Or a color in this case is a synonym for what? In this case, any given fixed color is a synonym for a more complex in its structure mathematical object called what? A linear permutation. In this case, it's an order-sensitive string that is built up on the alphabet of 2 distinct letters, E and O, with duplicates allowed. So look at this. With our 4 coloring, we actually created all 4 linear permutations of 2 distinct symbols where the duplicates are allowed: even, odd, odd, and even, odd. And in this case, we can see that because each such pairing, order-specific or order-sensitive pairing of these letters O and E is unique for each grasshopper, precisely because of that, our grasshoppers can never find themselves at 3 distinct vertices of a 2 by 2 square under no finite amount of legal jumps. But also, before we move on to another solution, guys, think about what other question did we ask? Well, again, I chose the mix. For example, in our case, I worked with this mix, red, green, and yellow. And we said that in this case, blue was out. But because of that, not only in no finite amount of legal jumps or in no finite amount of time, our 3 grasshoppers can find themselves at 3 distinct vertices of a 2 by 2 square, but also that means that these grasshoppers, no matter how they jump around, can never find themselves at a blue vertex or at a vertex whose parity of the components is shown over here. So in some sense, we also answered the following question. I could have posed, for example, a similar question. Given this initial distribution of grasshoppers, can they find themselves in the remaining vertex of the original parent unit square after they jump around for a finite number of jumps? The answer is evidently no. And again, we should understand that these colors can be mixed any which way. For example, we work with these colors. green, yellow, and blue, like these guys, it is evident that they will never reach the red point or any other mix. Pick any three. The remaining color point on our integer lattice will never be reached. Now, this is one solution, and for the curious travelers, I'll present two more solutions. One solution will be based on the problem-solving approach that we already studied, the reverse order, and another approach will be based also on invariant and a deeper notion that is actually quite hefty and goes into the heart and soul of the so-called, let's say, two-dimensional lattices that has to do with the so-called primitive triangles. Now, here's another solution of the same problem that answers the question posed in the negative. No, it is not possible for the three grasshoppers located initially as shown and then execute a finite number of legal jumps and find themselves at three distinct vertices of a 2x2 square, a solution that is based on the reverse order problem solving approach that we studied earlier. We remember that one of the perhaps pedagogical devices that we used was a movie camera. When we take a movie with a certain process, certain processes are reversible, certain processes are not reversible, and in the case when certain processes are reversible, we can play this movie, logically speaking or vaguely speaking, backward and obtain a certain result. And in this case, it turns out that the model of taking a movie and playing it back works, and here's what it means. Let's say our happy grasshoppers begin jumping around the orthogonal integer lattice Z squared, and every time they make a jump, I take a picture. Jump, picture, jump, picture, and so on. After n jumps and n pictures, I lay out all these pictures nicely for you and tell you this is the first picture, this is the next picture, and so on. This is the nth picture, and if I point you to any picture, you can tell me, okay, definitely this is the next picture with respect to this one, or previous picture with respect to that one. But here is the technical idea of the next experiment. Let's say I pick one photograph in the middle and throw out all the photographs on the right and all the photographs on its left. Without any context, I show you only one photograph and I ask you the question, was that photograph obtained when the movie camera was rolling forward in the forward flow of time, or was that photograph taken when the camera was rolling backward in the reverse flow of time? I claim that there is nothing in this world that will let you answer this question with absolute certainty. You simply will not know. And here what it means. Let's say our grasshoppers jumped around and then magically they found themselves again in the same configuration. It doesn't matter, it could be any one, but this is just a convenient starting point. You only see the picture of our grasshoppers sitting in the red point, green point, and yellow point. Question, was this picture taken when the camera was rolling forward in the forward flow of time or when the camera was rolling backwards in the reverse flow of time? You cannot tell because in the forward flow of time, let's say our grasshoppers, yellow, red, and green, was sitting right here in this. They were forming this triangle. And then in the forward flow of time, the green guy jumped into the green point. Roman took the picture, ka-ching, showed it to you. Wonderful. But when the camera was rolling backwards in the reverse flow of time, it could have well happened that our grasshoppers were sitting like this, red, yellow, and green, forming a totally different triangle like this, you see? And then in the reverse flow of time, it so happened that this red grasshopper flew backwards home over here and landed in the red point. Ka-ching, at that point the picture is taken and shown to you. How can you distinguish which way the time was flowing when this picture was taken? I claim that there is no way, and that is precisely what it means that in this case the jumps or any legal jump of any grasshopper at any time is reversible. In some vague vague analogy, in real analysis, we will say that the given function has a what? A continuous inverse. So what does that mean? Well, that means that setting up a contradiction, we assume temporarily that, let's say, after some miracle combination, miracle sequence of a finite number of jumps, our three happy grasshoppers found themselves sitting at the vertices of three distinct vertices of a 2 by 2 square. Which one? Which square can you guys see nicely? Let's say yellow square, this, and this, or this, and this. Which three vertices of such a square, three distinct vertices they occupy, does not matter. Again, we put our conscience to the side, we throw our conscience to the wind, because we know this is impossible. If one grasshopper of the correct color, let's say, can find itself in a, let's say, yellow, in a node of the given orthogonal lattice of yellow color, then the other two have to betray their colors, and they cannot do that. This is nonsense. We prove that. But let's say we throw caution to the wind. Okay, this is possible. So what does that mean? On the one hand, we already proved in the previous segments that if that happens, then the only nodes that our grasshoppers can visit when they jump like this are the nodes that are generated by that square. In other words, if it so happens that our three grasshoppers found themselves at three distinct vertices of a yellow, let's say, 2 by 2 square, that means they can only jump around the lattice that is generated by this 2 by 2 square. They can find themselves only in this type of lattice points. And number two, on the other hand, precisely because the jumps are reversible or time reversible, if we start playing this magic movie backward and leading us to the initial configuration, it means that somehow our grasshoppers will jump their way backward into the original configuration, where they sit at the red, green, and yellow vertices of the 1 by 1 unit square. But that is precisely the contradiction, because the 1 by 1 square cannot be legally fitted onto the lattice that is generated by 2 by 2 square. If anything else, the distance between any two immediate vertices of a 1 by 1 square, which is 1, is strictly smaller than the distance between any two immediate vertices of a 2 by 2 square. Definitely 1 is strictly less than 2. And that is impossible. Yes, we can somehow try to place one vertex of our square in one vertex of the 2 by 2 square, but then there is absolutely no way we can fit that 1 by 1 square onto, somehow stretch the 1 by 1 square or contract the 2 by 2 square. This is nonsense. This is mathematical absurdity, impossible, contradiction. Hence, here is another way that shows that the answer to the question posed in this problem is no, in the negative. It is impossible for the three grasshoppers initially located in the three distinct vertices of the unit square to execute any finite number of jumps and find themselves in three distinct vertices of a 2 by 2 square. Before we discuss so-called prime or primitive or fundamental triangles and prime or primitive or fundamental parallelograms, forget about all this orthogonal integer lattices, the squared mumbo jumbo. Go back to middle school and I'll give you a hint. Book 1, proposition 37, if I'm not mistaken. Look it up. Euclid's Elements, book 1, proposition 37, 1, 2, 3, go. And this is one invariant that you were actually also expected to find. And if you did not find it, then you need to go dig up your middle school plane geometry books and refresh the information that you studied there. But let's say in total isolation from all these integer lattices, orthogonals, Z squared, and all this stuff, all this jazz, take any triangle, let's say triangle ABC, doesn't really matter. Let's say this one, and let's call it ABC. Now we conduct the following transformation of such a triangle. We take any which vertex of that triangle, and then we reflect it in the opposite side. For example, let's this way, and then we go, well, we do not reflect it, we do what we are told to do in this. We mimic the jump. We extend the line, then we produce the point A prime such that the distance AB is equal to the distance BA prime. So far so good. This is precisely so our grasshopper flew over here. Now we have what? Now we have, instead of triangle ABC, we have a triangle that is what? A prime BC. So this is our triangle. Or maybe let's hatch it that way. Question: what can be said about the areas of the triangles A, B, C and the triangle A prime B, C? Well, the answer is, under this transformation, the areas are exactly the same, or the area of the triangle ABC under this transformation, as described, is invariant. Precisely. How can we prove that? Well, this is where the book 1 proposition 37 comes in. The triangles on the same base but in the same parallels have the same area, or as Euclid puts it, equal one another. That's his way of saying these two mathematical objects have the same area. So what is the area of this triangle ABC? It's the length of the base. Now the points that remain stationary under the jump will delineate the base. And then how do we construct the height? Well, we drop a perpendicular, so this will be the height. The length of this height times the length of the base over 2. That's the area of our triangle ABC. What's the area of the triangle A prime BC? Same exact spiel. The length of the base, exactly the same. And what is the, how do we construct the height of this triangle? Well, the height of this triangle, again, we draw a perpendicular to the base BC, perhaps extended, and here we have it. But what can we say about this line segment over here and this line segment over here? Well, look at this. The interior angles at B in this case are what? They're vertical, and they are the same. As Euclid claims, all right angles are equal each other. In modern times, this is only partially true, because all equal angles are equal each other by magnitude if the angles are not oriented or not directed. When the angles are directed, then positive pi over 2 versus negative pi over 2 are two very different things. But in this case, okay, we're only care about the magnitude. So vertical angles are the same, right angles are the same. That means two angles in these triangles are the same. By the corresponding theorem, the third angle, like this angle, for example, and this angle is the same. So what do we have? By definition, AB, the distance AB, is equal to the distance BA prime. So what do we have? Angle, side, angle, and then angle, side, angle. By this criterion, the triangles shown over here, this one and this one, are congruent. That means that the lengths of the sides that lie opposite the corresponding equal angles are equal, so the heights are the same and the bases are the same. Evidently, the area of the triangle ABC is the same as the area of the triangle A prime BC. So this would prove that without any of these orthogonal integer lattice Z square mumbo jumbo, under any legal jump, the area of the triangle that is delineated by the positions of the grasshoppers remains what? Invariant. Wonderful. That means that the magnitude of this invariant initially is what? 1 times 1 is 1 over 2, 1/2. And if the square, the destination square is 2 by 2, what is the area of the triangle that is formed by any three such vertices? Well, 2 times 2 is 4 over 2 is 2. Is 2 the same as 1/2? No, it is not. 1/2 is not 2. 2 is not 1/2. Contradiction. This is impossible. So in some sense, this is a 30-second solution of this problem, but the reason I didn't give it to you guys up front, because then we wouldn't learn anything useful about this wonderful device called Orthogonal Integer Lattice Z squared. So this is yet another invariant in this case. But the situation here actually goes much deeper than that. And this is where the so-called prime, primitive, or fundamental triangles come in. So what is a prime triangle? A prime triangle on a lattice is a triangle whose vertices are precisely the nodes of the lattice, but it's a triangle that does not contain any nodes of that lattice inside of itself and does not contain any nodes on the sides of the triangle. In other words, here is a triangle that is primitive. You see, this is a prime triangle. Here's an example. And in our case, our initial triangle delineated by the initial configuration of the three grasshoppers is such a triangle as prime, primitive, fundamental, basic, whatever good name you can think of it. Wonderful. And it turns out that you guys should do some more research on your own, but the family of prime or primitive or fundamental triangles is fairly rich. For example, we constructed such. This is one, for example, prime triangle. Here is another one, and here is maybe another one. You guys should try to find other ones. And what are the examples of definitely not prime triangles? Well, take this guy, for example, here, here, and here. This triangle is not prime. Why? This triangle is not prime precisely because it contains the points on its sides. This is no go for a prime triangle. Here is another triangle that is not prime. This one, look at this. This triangle is not prime because inside of it there is a node of a lattice, and on one of its sides is a node of a lattice, not a prime triangle. Now, these prime triangles go into the so-called prime or primitive or fundamental parallelograms. The same exact spiel. Look at this. Here is a prime parallelogram. This, and this. You see, this parallelogram here is called prime precisely because its nodes are the vertices of that parallelogram are the nodes of the lattice, but neither its sides nor the interior contain any nodes of that lattice. That is important. We can construct other, for example, this parallelogram, see, the larger one, this guy. Not a prime parallelogram because two of its sides contain the nodes of lattice, no go. And from here, there is this small theory keeps rolling for the integer lattices. For example, it can be shown that the area of the prime triangle on any given lattice is precisely what? Invariant. And on the unit, on the unit square lattice is precisely 1/2. 1/2 is the area of any primitive triangle. And then from primitive triangles, we can put together what? Primitive parallelograms, obviously. You see that, right? In two ways, this way or that way, and take it from there. So how does this fit into another slightly more deeper or mathematically hefty solution? Well, look, initially what we have is what? Is a triangle that is prime, because there are no nodes of the corresponding lattice inside or on the sides of that triangle. Now, here is the statement. Under any legal jump, the resultant triangle will also be prime, primitive, or fundamental. In other words, let's say over here, the red grasshopper jumped over the yellow one over here. What do we have? Fundamental, a fundamental triangle, and so on under any jump. How can we prove that? Well, the proof over here is relatively straightforward, but it takes some time to develop the knack to see this proof. So here is one way to prove it. Let's say our original triangle was prime or primitive or fundamental. Let's say this guy. And then the green grasshopper jumped over here. So this distance remained the same, but the distance between the green points is 2 units. So this distance equal to this distance. So this guy jumped over here. So what do we have now? Do you guys see what's going on? Where this is going? Look, we have new piece, new piece. What is this? Precisely, this is 1/2 of a primitive, what? Primitive parallelogram. This guy, exactly. And here's another wonderful property of lattices that are built as I explained. Under any parallel translation along a vector that originates at a node of a vertex and terminates at a node of a lattice, this lattice is taken into itself. That means that if initially we had, for example, look at this and this and this, from this triangle we can double it this way. We have our what? A primitive parallelogram. And under the translation this way along this vector, this parallelogram, which is primitive, is taken into this parallelogram. But under this translation, as we know, the integer lattice is taken into itself. It means that a primitive parallelogram is taken into a primitive parallelogram, no points inside or on the sides that delineate this parallelogram. And evidently, we can always put together such a primitive parallelogram with a corresponding choice for the rectangle and the triangle, and that triangle will be precisely the destination triangle, and such a triangle will be primitive, prime, or fundamental. It will not have any nodes inside or on the sides. And this is our elegant and fairly hefty chain of units of mathematical knowledge that we string together for another negative answer to this problem. So summing it up, prime or primitive or fundamental triangles, we show that under any jump, a prime triangle is taken into a prime triangle. And we know that the area of all prime triangles on a given lattice is invariant. It's a constant for that lattice. In our case, it will be 1/2. Again, we come back to our middle school observation, which did not require all that knowledge, but I just wanted to share this bit of knowledge with you so you guys can do some more investigation on your own, and that is the direction. As such, under any legal jump, if we started with the configuration of the grasshoppers that corresponded to a prime, primitive, or fundamental triangle, we will have a prime, primitive, or fundamental triangle after any legal jump. The area of such a triangle is a constant for that lattice, 1/2, and that means that the area of a triangle that is delineated by the 3 grasshoppers that find themselves at 3 distinct vertices of a 2x2, 2x2 square will be what? 2 times 2 is 4, over 2 is 2. Again, we come back to this. Cannot be equal to 1/2, and that is yet another proof that the answer to the question posed in this problem is in the negative. Now that you guys know what's going on with this, you can do some more investigation. There's actually way more things that you can try to prove. For example, combine the information that we already discovered during this episode, that the jumps are reversible. And for example, it looks like a childish observation, but it is actually quite helpful. Look at this. Remember when we discussed the fact that what varies, the distance between the grasshoppers under their legal jumps can grow, and that is the case. Let's say our grasshoppers were in this position right here, in this position. Remember, this distance is what? Let's write it down here, 1. This was square root of 2, and that distance right here was square root of 5. Remember the situation? Okay, now precisely because the jumps are reversible, now it looks like it is always possible to put our prime or primitive or fundamental triangle shown here into a triangle where the length of the largest side will be smaller than the largest side in the previous triangle. What does it mean? Well, here the length of the largest side over here is square root of 5, evidently. But what is the algorithm in this case? The algorithm in this case is the following. We detect the largest distance between two grasshoppers, and we execute, for example, we grab this guy and we flip him over the other one, not the one that delineates the largest distance, but the other one, and we put him over here. And now look at this. What a miracle. Now our numbers go like what? 1, 1, and square root of 2. And square root of 2 is definitely less than square root of 5. So this way we can, intuitively speaking, make the triangles smaller on demand. In any case, we can pick the right grasshopper to move and shrink, so to speak, a primitive triangle, and so on. Now, this is it for the mathematical problem S2M49, and we will move on to a new challenge next. Our next challenge will be a problem in mathematics numbered S2M50, and in that problem we're given 666 trees that are located on a circle. We're not told how they're sprinkled over the periphery of that circle uniformly or not, so we can take this under advisement, but this is the deal. And initially, on these 666 trees that are located on the circle somehow, there sit 666 flying squirrels in the fashion one flying squirrel per tree. One flying squirrel per tree, 666 trees located on a circle. This is the initial time, and then click, the timer goes, and every second the following process unfolds. Any one random flying squirrel jumps from the tree that it sits on to the immediate, you see there are no trees over here, immediate neighbor, clockwise, in a clockwise fashion, from one tree to the immediate neighbor clockwise, and some other random flying squirrel jumps from the tree that he or she sits on to the immediate neighboring tree, counterclockwise, in opposite directions. For example, one squirrel flies from this tree to this tree over here, and somewhere here another tree. If this guy flew this way, then this guy will fly this way from one tree to another. And the jumps are made not over one tree or some trees, but to the immediate neighbor. No trees in between, from here to here, and let's say from here to here. Every second that process happens. One flying squirrel flies clockwise, the other squirrel flies counterclockwise, one span only. One span between any two immediately adjacent trees. And the challenge in this question, again, this problem is open-ended. The challenge and the question in this problem is the following. Can it so happen that after a finite number of time, or after finite number of these double jumps, all squirrels will gather on a single tree, on one tree? This problem, again, as it is evident by its placement, can be solved using the invariant problem solving approach. And again, this problem is open-ended. If you think that the answer to this question is in the positive, then the burden of producing at least one winning sequence of how that can happen is on you. You have to produce it. And if you think that the answer to this question is in the negative, then again, you have to generate a convincing proof that no matter how flying squirrels fly around, clockwise and counterclockwise, they can never sit or gather on one tree only. Good luck with this problem. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will share my solution of the mathematical problem S2M50.